Imagine you're running a soup kitchen, but with a twist. You've got two big pots of soup, Soup A and Soup B, and every serving is a bit unpredictable. Today, we're going to look at an interesting probability problem called soup servings from LeetCode, where the challenge isn't about cooking, it's about calculating the odds that Soup A runs out before Soup B. Let's dive right in. We start with two soups, A and B, each having the same amount, n milliliters. At each turn, we randomly choose one of 4 serving patterns, each with equal probability. Serve 100 milliliters from A and 0 milliliters from B. Serve 75 milliliters from A and 25 milliliters from B. Serve 50 milliliters from A and 50 milliliters from B. Serve 25 milliliters from A and 75 milliliters from B. If a serving pattern asks for more than what's left in a pot, we just serve whatever remains. The process stops immediately when either soup is empty. We want the probability that Soup A empties before Soup B plus half the probability that they both become empty at the same time. That's our final answer. Let's take a small example, n equals 50 milliliters for both soups. From the start, we could pick any of the 4 serving patterns. If we pick the first pattern, 100A, 0B, Soup A instantly becomes empty, B still has soup, that's a full success for our calculation. If we pick the second pattern, 75A, 25B, again Soup A becomes empty instantly, full success. If we pick the third pattern, 50A, 50B, both soups become empty at exactly the same time. This is a tie, so we only count half of that outcome toward our probability. If we pick the fourth pattern, 25A, 75B, Soup B becomes empty first, that doesn't count at all. Since all 4 patterns are equally likely, 25% each, our final probability here is 0.25 times 1 plus 1 plus 0.5 plus 0 equals 0.625. This means there's a 62.5% chance that A runs out before B, with ties counted as half wins, in this scenario. The challenge is that for larger n, the game might last many turns. After each serving, we could be in many different possible states, different amounts of soup left in A and B. We can think of the problem as a probability tree. Each state is defined by how much soup is left in A and B. From each state, there are 4 equally likely branches, representing the 4 serving patterns. The process continues until one or both soups are empty, at which point we know the outcome and can assign it a probability contribution. Instead of simulating all possible paths, which would be exponential in size, we use recursion with memoization. Define a function p, a, b, equals probability that A empties before B plus half probability both empty at same time, starting with a ml of A and b ml of B. Base cases handle when A or B is already empty. The value of p, a, b, is the average of the values from the 4 possible next states. Memoization stores each, A, B, result so we don't recompute it, making the approach efficient. Also, since all serving amounts are multiples of 25 milliliters, we scale n down by dividing by 25 and rounding up, dramatically reducing the number of states we need to consider. For very large n, the probability approaches 1, so we can directly return 1.0 without further computation, as the error becomes negligible. After scaling, if u equals ceil, n divided by 25, we have about possible states. Time complexity, O, U square. Each state computes in constant time from 4 transitions. Space complexity, O, U square, for storing memoized results. The key trick here is normalizing the problem from milliliters to 25 milliliters units to keep the state space small. The recursion directly models the probabilistic process, but memoization transforms it from exponential to polynomial time. The symmetry of the serving operations and the fact that A's depletion is slightly more likely than B's leads the probability toward 1 for a large n. The problem is essentially a Markov chain hitting probability problem disguised as a soup serving game. And that's the soup servings problem. We started with a simple example, built up the recursive thinking, optimized it with memoization and scaling, and saw how the probability creeps toward 1 for large amounts of soup. Problems like this are a perfect example of how recursion and probability can work hand in hand. If you enjoyed this breakdown, hit that like button, subscribe for more deep dive explanations, and I'll see you in the next one.